Hi again. In this lesson, we're going to continue our chi-square tests, and we're going to do tests of homogeneity and independence. Okay, so let's talk about that. And so with the one we did in the last lesson, goodness of fit, that gives us 3 tests. So first thing I want to do is distinguish between these 3 tests. So all of these use multiple proportions, so more than 2, and they have, here's what they have in common. The null is always independent, no association, or the same distribution. Okay, so let's come back to that after we talk about the different tests here. Okay, so the one we did in the last lesson was called a goodness of fit test. Now that one uses one categorical variable. So we have one variable and we're comparing it against a claimed distribution, right? So remember we did that with the jury pool in the last one with the demographics for race and ethnicity. Okay, so we have some kind of claimed distribution. It could be uniform, which means it's all the same, or it could be some specific distribution that we're given, okay? But we have one variable, okay? Let's look at homogeneity. Okay, so think homo means sameness, right? Homogeneity. So we're testing, again, one categorical variable, but this time we have several subpopulations. Okay, so we want to see if these subpopulations are the same, okay? Same distribution, okay? Usually we have a random sample from each subpopulation. So this one should be multiple random samples, right? So I'm going to put a note there. Okay, versus one big sample. Okay, so we have subpopulations. Okay, the third one is independence. And here we're comparing 2 categorical variables. And we've looked at independence before, especially in 243. Now we're coming back to the official hypothesis test for independence, which is really exciting. Okay, so we have 2 categorical variables. Remember how we had a contingency table last time? And we're going to see whether the variables are independent or not independent. This one's usually from a single random sample and sorted into all the categories, okay? So this one's usually one random sample. Okay, so you're starting to get a feel for the difference between these 3. So goodness of fit and homogeneity both have one categorical variable. Goodness of fit is one set of data compared with a claimed distribution. Homogeneity is that one categorical variable, but for multiple random samples. Okay, so you might have multiple rows, or I suppose it could also be multiple columns. And independence, you have 2 categorical variables. Okay, so we're going to practice, in just a minute, we're going to practice distinguishing between these. But first of all, let's go back to the null, because when you're writing out the hypotheses, I find it really helpful to just have a sense in my mind of what the null is going to be, okay? So remember, the null is dull, or no effect, right? So that's kind of what we're going to assume, is that there's no association, which is also the same as independent, or the same distribution, okay? So we're always going to assume that in our null, and then the claim will be that there is a difference. Okay, so we'll come back to that a little more detail in a moment. But first of all, here's a practice problem. So I think it'd be great for you to take a moment and pause this and see if you can underline the key words and phrases and determine which of these 3 each one is, okay? So take a minute to do that, and I am going to continue here so you can come back and check your answer. Okay, so determine which of the 3 tests should be used. A, we want to see if there's a relationship between gender and healthcare coverage. And we're talking covered or not covered. Okay, so relationship, that seems like a key word. Also, we have gender and healthcare coverage. So we have 2 variables here. And then relationship really goes with the word independence. Okay, so if you said independence on this one, you are correct. Okay, let's look at B. The program dean wants to compare the final grade distributions for 3 different instructors to see if they're the same. Final grade distributions, 3 different instructors. This tells me this is subpopulations, right? Populations. Okay. Okay, and then this is one variable, the grade distribution, versus gender and healthcare coverage. Final grade distribution is just one variable for 3 different instructors. So if you said homogeneity, you are correct on that one. Okay. A trading card company claims that 5% of cards are rare, 20% are uncommon, and 75% are common. We want to check this claim. Okay, so here we're given a distribution, right? They're saying 5% is rare, 20% is uncommon, 75% is common. And probably we're going to have to get a sample of these cards and compare that distribution with this claimed distribution, right? Okay, so if you said goodness of fit, you are correct. So let's write, we have a given distribution for this one. And another thing we could say is that there's a single variable or one variable. Okay. Okay, great. Let's keep going with an example then, okay? Okay, move this up. Okay, great. So here is another example that we'll go ahead and do a full test on, okay? So a random sample of adults in the US was taken in March 2012, and each was asked whether they approved or disapproved of the job being done by President Obama, Democrats in Congress, and Republicans in Congress. The results are shown in this table. Oh, I don't know if I have this table numbered. We would like to determine if the 3 groups and the approval ratings are associated. Okay, so first of all, what type of test, which of these 3 tests is this going to be? So here's another chance for you to distinguish. Okay, so let's do the key word. So one thing I notice is it says a random sample. So that tells us it's one sample, which could kind of narrows it down a little bit. But then also we have how many variables do we have, right? And we can look at the table, we can look at the wording. So we have approved or disapproved, right, of the job being done. And then we have kind of 3 different jobs. We've got the president, this is back when Obama was president, Democrats in Congress, and Republicans in Congress. So here we really have 2 variables, right? And we can kind of see that over here. We have one variable is approve or disapprove, and then the other variable are the groups. Okay, now you might be thinking, well, this is subpopulations, but I wouldn't say subpopulations because they're saying they took one sample, right? So we're kind of testing the survey of adults, right? This was a random sample of adults, U.S. adults, and then they were asked whether they approve or disapprove of these folks. So it's one sample that was sorted into these categories. And then the other key word here is associated. So associated goes with a test of independence because we're talking about 2 variables and are they associated, okay? So I could have also highlighted this down here. We'd like to determine if the 3 groups and the approval ratings are associated. So there's our 2 variables. oops, two variables. And so associated means independence. Okay, great. So we're going to set up a test for independence, and then I'll show you how this test is going to work. Okay, what type of test is this? So I wrote up here independence. Right then, we'll put it in the hypotheses as well. Write the hypotheses for this test. So for H naught, remember going back up to the very top, the null is always independent, no association, or the same distribution. Okay, so we're going to say they're independent, there's no association. The approval ratings and jobs, I'm going to call those three different jobs, are independent. I'll just put no association. Okay, and so the alternate, HA, will be the opposite of that. The approval ratings and jobs are associated. Okay, so keep in mind, so if we'll be looking at some probabilities here, and if there is no association, we would expect that the approval and disapproval ratings would be the same, right? That's why the null is always the same distribution or independent or association, no association. Because if they're independent, we would expect the approval and disapproval to be the same for each job, right? If they're not the same, then they're dependent. So different is dependent. You might remember that from comparing probabilities in a previous independence test. Okay, so hope that's making sense, and we're going to go over to stat key now. I'm going to switch to the next page of my notes here. Okay, now let's go to stat key. Just like with the goodness of fit, we're going to have expected counts. So I'll read the directions first before I go over to stat key. Let's first use stat key to calculate the expected counts for each cell in the table. Okay, then we're going to form the chi-squared, remember that's Greek, chi-squared test statistic, and the contribution from each cell. Okay, so I've got some instructions here that I will do over in stat key. Okay, so here's my stat key, and remember we're down here in the more advanced randomization tests. So last time we did the chi-square goodness of fit. Now we're going to do chi-squared test for association. Okay, and there are some built-in data sets, but this is not one of them. And so what we're going to do, you can see how this is both in independence and homogeneity. These are both two-way tables, right? So they will have rows and columns. That's what makes it a little different from the goodness of fit test. So I can do show data table. This is not super useful because it's, oh, hold on, let me pause one second. Okay, yeah, for a moment I couldn't remember if this table was built in, or the one we're going to do is built in or not. But notice how they have the category 1 and category 2. So instead of having, this is a different way of organizing the data. So what we're going to do is go into edit data and enter a table kind of like this, okay? So in the notes I have for you already written out, typed out what the input looks like for this data set. So you can see it's like a table. The upper left is blank, and then we have Obama, Democrats, Republicans, and then the approve row and numbers, and the disapprove row and then numbers, okay? So what I suggest is opening up the Word doc of the notes, if you don't have it open already, copy this bit and paste it right into stat key. Okay, I don't have mine open at the moment, so I'm just going to type, but you're welcome to fast forward through that part or go ahead and just pause it and get the data or type it yourself. Okay, I'll just type it this one time. Okay, so I'm just going to keep that blank right there. And you'll notice there's commas between each one. So we've got a blank, then we have Obama, Democrats, Republicans, enter, approve, comma, 842, comma, 736. I'm also putting a space after each comma. I don't know if you have to or not. And disapprove, comma, 616, 646, and 842. And it looks like I need another P in disapprove. So we got that. Okay, so raw, I have some options here. Raw data, data has header row. Okay, it's not the raw data, it's tabulated already. So I'm going to try this and see if this works. Okay, great. So let me go back to the notes again. Okay, so we've got that entered, and here's what it looks like. I put a note here to not enter the totals. So sometimes you'll see, and in fact in this table, we also have the total row and column, but it's not smart enough to know those are the totals. So if you enter the totals, it'll think that's another category, and that'll mess things up. So don't need to enter the totals, just the interior, the headings and the interior, which is kind of nice. And then check that the totals match after you hit OK. Okay. And then let me just double check up here and make sure I did all this stuff. So we selected chi-square test for association. Okay, notice that the null hypothesis is set at no association. So let's look at that. Select edit data and then enter the data or copy paste. Okay, great. So we did that. We'll just go back and double check the yeah, so this is nice. It builds in the null for us as no association. So it knows kind of what we're doing. Okay, so let's take a look at the notes here. So we have, this is what our data should look like. If you go to edit data and just to double check, you should see that. And here, this will be a good reminder for how to set these up like this, okay? And then we want to just double check our totals, okay? So let's go back to stat key and double check. I think I need to get this total over a little bit. Let's double check. So I'm getting 2,119, 2,104, 4,223. And going across the bottom, 1458, 1382, 1383, and 4223. Okay, great. So I want to make sure that that is all matching. Okay, so we checked our totals. That is excellent. Okay, so now we can go ahead and do a simulation. So here's a screenshot down here. So let me go back over here. We've already got our null, we've got our data set, so we can go ahead and generate 2,000 samples. Okay, and similar to the goodness of fit, this is really a measure of how different they are, right? Because remember, same, no association is same. Same proportions. So that would be a very small number, right? So, and I'll show you how we get this chi-square value. But we want to determine, this is our test statistic. So again, it's going to be a right tail test, just like the goodness of fit, where we will see, okay, how likely or unlikely is it to get this chi-square value? And you can see that it's way, way bigger, 106 compared to what popped up as 7 point something. So let me type this in, 106.351. Okay, and you can see that's practically 0, okay? So these do appear to be quite different, as you might have expected, just because of the difference between the Democrats and Republicans in the time of Obama, which has really just even grown larger since that time. Okay, so if we just did Obama and Democrats, that might be more similar, but between those two and Republicans, quite a bit of difference, okay? In fact, if you're curious, test just Obama and Democrats and see if there's an association there. That would be an interesting test to do. Okay, so let's go back to the notes and see what we've got in this screen share here. Okay. Great. So it looks like I didn't do the full simulation yet, but that's okay. Let me see, what did I highlight on this page? So yeah, we want to just keep in mind that this is our null. Our null is no association. And then this is our chi-squared test. Test statistic. Oh my gosh, that's hard to say. Test statistic. Okay, and then remember this down here is just the last sample generated, the last simulation generated. Okay, so we'll come back to our p-value and everything, but I want to go ahead and show you how this chi-squared value is calculated, okay? So I'm going to do that in the next video, so I'll see you there.